Welcome to Engineering Drawing with SOLIDWORKS. I'm John Fielke, and in this topic I'd like to present geometric tolerancing. So geometric tolerancing is another topic related to engineering drawings. So you see we've done looking at size, we've looked at shape. Now we want to look at the next part, which is about the total geometry. So there's quite a lot of pages in the AS 1100 standards. You can see here there's quite a lot of references, several hundred pages or nearly 200 pages of information about how to do just geometry tolerancing. So it's quite a complex issue, but I would just take you through some of the basics of geometry tolerancing so that you know that it exists and you're able to read and understand, know where to look to find what these symbols and information means. So at the end of this presentation, I would like students to be able to explain the need for geometry tolerancing, explain the different types of geometry tolerances, and to be able to interpret the geometry tolerances using the principle of independency. So, geometry tolerances. What is it? Why do we need to know about it? Well, it might be the correct size, but is its actual shape and functionality really correct? So, we use geometry tolerances for things like flatness, straightness, circularity, cylindricity. Because we've talked about size, but say if we've got a circle, size is just purely about the diameter. It might wobble around in here, and that becomes the geometry tolerances. We'll talk more about that. The orientation, profiles, position, virtual conditions. So there's a whole lot of aspects here about geometry tolerances, and we'll just go through some examples. So we're buying a pool table. There's a cheap pool table, there's an expensive pool table. It might be the same size, but what might be the difference? What's going to make a pool table function as a really good pool table? And one of those is going to be what do you think? It's going to be the flatness, isn't it? It's going to be how flat that surface is. Now, if we looked at there's legs on here, we can adjust the position, we can adjust the height to be level at certain places, but it's really that flatness so the ball runs straight. So geometry tolerancing is very important for a pool table. So we're after flatness. So it's not a function of the leg height, it's a function of, if you balance it out, is there dips, is there curves in that table? We're going to the timber yard and we're looking at timber. Maybe some of you have gone and purchased timber there. Most people will look at one geometry tolerance. Yeah, they'll be all the right size, you'll have the right width, the right thickness, all the way along. You can go along and measure it's correct. But people might choose it for another geometry, and that could be straightness. Is that you look down there and see, is that timber straight? So you line it up, and we want straightness, not just size and shape, but we want straightness. So we can specify that with a geometry tolerance. Another one here is with a hydraulic cylinder bore, is that we need, if we've got this, there's a seal in here to stop the hydraulic oil under pressure going past the piston. Now, for that seal to seal, we don't just need it to be equal distance, we need it to be very round. So we need circularity in this one to actually have that to seal as that moves along, as the piston moves up and down. It needs to move in a circular shape, not just of the right size, but it needs to be circular within a certain tolerance range. Here's another one. If we want this cam to operate correctly, we need to have that profile just right. So we need to say, with a geometry tolerance, we can say how accurate that needs to be to the profile for that to work. So there can be a profile tolerance here. So you can see the way geometry tolerances work. Another one, this is on a drive shaft and a yoke. So we've got an axis through here, we've got another drive axis here, and for this to work properly, we need them to be within a certain range of perpendicularity. So we can put the dimensions are right, but they need to be also with the correct geometry tolerance there, so with being perpendicular. So that's another tolerance that we want. So here's going into some detail. So here's measuring flatness. So what we're interested in is how flat is this top surface. So what we need to do is actually line up, place a flat surface here, and actually have some system that takes a dial and it passes all over this surface. Might have a virtual dial, which now is a laser that passes over there. It can measure that surface. And what we're saying with our symbol, so we can actually say, here's the surface on the top. We have a tolerant geometry tolerance box. We have flatness as the symbol and saying it must be flat within 0.3. So it means if we've got this plane, that all the points on that plane must lie within this band here, this 0.3 of a millimeter band for that flatness. We also have a general tolerance, so it can be within 29.5 millimeters high to 30, but we're also adding, there's a flatness, so we don't want it coming outside of that range. So we can add a flatness symbol to our surface. Straightness. So here's a symbol here for straightness. So we don't want to just measure the points all the way along, we want to know how straight that is within here. So a curved beam is not going to be acceptable, even though all the dimensions are right. So we can have a straightness tolerance here. So it might have to be straight within 0.05. You might be happy, if you're at the timber yard, you'd definitely be happy if it was within 5 millimeters of being straight. Some of those might be 50, 100 millimeters curvature on them. So there's straightness. Circularity, as I mentioned, you can see here's a circularity tolerance, and it says that all of the surface must lie within a variation of 0.07 of a millimeter of there. So that's circularity. Cylindricity is another one, which is saying not only is it circular, but it must be circular along a certain plane there. So we can have cylindricity tolerance. So you can see engineering drawings, you might have thought, oh, this is really simple. There is a lot of information. It is really a language that is between the designer and the manufacturer. And there needs to be people in between that say yes or no, does it meet the designer's specification? If not, must be reworked or discarded. And people can work for weeks machining items and they just might be out with their tolerance and it might just have to start again. And that can be very expensive from the material and the time point of view. So here's a list taken out of the textbook of some of the different geometry tolerances and their symbols. So it's a consolidation of what's in the Australian standards, which also follow the international standards. So you can see those different symbols and the words there. So for some of these tolerances, geometry tolerances, we need a datum to refer to. So if it's going to be perpendicular, what's it going to be perpendicular to? So we have datum faces. So you can see here, here's a datum. It's got the symbol A with a line pointing to a surface here. And it's saying, here's surface B. So it's saying, here's B is perpendicular within 0.2 of A. So you can see A is in here. It says surface B, or datum B, is perpendicular within 0.2 to A. Here's also another datum, C, that they've shown in here. So we use uppercase letters for datum faces, so they're in a square box. And SolidWorks allows you to add them in to the drawings. So here's our perpendicularity. So if we're going to say a face is perpendicular, you need to say perpendicular to what? So it says perpendicular with that symbol, the amount, accuracy of the perpendicular, and then the datum face. And here's datum face A. So it's saying that face must be perpendicular to that face within 0.05 of a millimetre. We can have parallelism. So again, so you can see this symbol is referring to this surface must be parallel to this surface, which is A. You can see the link there. Angularity, so you want to say it's this angle is related to this datum A. So we have those parts as well. Profiles, as I showed with the cam, we can show how accurate the cam surface must be with a profile symbol. Now, position. If we did linear position, like here, this is actually inch dimensions, but it's just a dimension. If we use just those, it would be acceptable for the circle to be plus or minus so much in a square. But actually using a position accuracy says no, it must be accurate within a circular point. So it can only go the radius distance out, not out to a square distance. So that's a little bit different also with positioning holes. You might say, what is the radial distance you want that hole to be from your ideal position, rather than X and Y dimensions, which are further away from that hole. So here's the tolerance frame. So for adding geometry tolerances, there's a frame, and we build that up in SolidWorks, and we'll show that in a minute. Here's looking back on here. These are actually electrical components, so printed circuit boards. They use a lot of geometry tolerances because they need a robot to pick up those parts, take the robot, put those parts on top, and they need to be very accurate. All those wires and legs must accurately be located for that to work. So there's more geometry tolerances on electrical components than there are on many mechanical components. So I think with that, we will have a look at SolidWorks and how we place these on there. So here I am in SolidWorks. I've got SolidWorks open. It's a drawing from the previous presentation. So I've just got a square surface here. But to show you how we add tolerance frames in, so we've got these tabs here. We can go to annotation. We can add in a datum feature. So if I click in datum feature, I can bring datum, and you see it snaps. We don't want to place the datum on our object, we put the datum outside. And the next one, you can see how it just adds the next datum in, so I can create datum ABC. Now, if I don't like those, I will hit escape. Now, if I only want B there, but the norm is that we start with A. So, oh look, that's a B. I want to change that. I can click on there. You can see label settings. I can change that straight away back to A under that label setting. So there's my datum setting. So up the top here, you see we've got datum feature. We can add that. Now we can add our tolerance frame in here. Just above the datum is our geometric tolerance. So I can bring up my frame and I can choose the symbol. I might want it to be flat on that surface within 0.1 of a millimetre, and then I can take that and I can say that surface needs to be flat within 0.1 of a millimetre. So we can build up our frame. We can change the symbols here, circularity. We can make it, so there's a circular one, not this is circular, but you can just change those values. And we can build up our tolerance frame here with those boxes. So we get a preview, and then we can place them on the drawing. So that's our placing geometry tolerances on a drawing. It's quite simple to create in SolidWorks. It's a little bit more difficult to understand and interpret And we really need standards and textbooks to help us with that. Okay, so back to our presentation. Now, the principle of independency. So we have dimensions with tolerances, we have geometry tolerances, and it says that we must meet both of those conditions. So one doesn't overrule the other, they all must be met with our actual part. So you can see here, here's a drawing of a pen. So we've got this line of symmetry, so we know it's going to be a circular part, so it's going to be a pen here. So we actually say this part must be within a certain diameter, must be within a certain circularity, and it must be within a certain straightness. So it's not just meeting one of those conditions, all of those conditions must be met. If it's not, that part is not satisfactory. It cannot be accepted as being suitable for our application. If you say, oh, well, it's outside and it's still suitable, well, then maybe you should look at what values you've got and whether you need such precise values in there as a designer. So they're very important. When you're putting these values on, you are saying accept if it's within the tolerance, reject if it's outside of those tolerances. So how do we measure these? Well, these days we have coordinate measuring machines which can be contact and non-contact, but most are still contact. And we have one of these machines quite similar to this machine here on the left in our building M laboratory. So there is a fine tip on the bottom where an operator will drive that up to a surface, drive it along a surface, and it will measure those coordinates on there. So we have that, it then gives us the values of that surface. So we can ask how flat is it, how round is it, how cylindrical is it, and it will tell us what those values are. So some of you might have already seen these machines in our metrology lab, but there's plenty of pictures on the internet. So these machines can be quite small. Ours has about 1 metre by 1 metre bed, but there are much larger machines as well for measuring coordinates off of larger systems. But we are going and moving to laser measurement as well as another technique. So if you'd like to see how a coordinate measuring machine works, you don't need to wait to come and see one in class. Have a look on just YouTube. There are many, many examples of coordinate measuring machines. And essentially people have jobs using these machines. They get a drawing, it has those tolerances, size tolerances, geometry tolerances, and people's job are to say, does it meet that tolerances, does it not? And essentially the answer is just a yes, we accept, no, we reject. And so that person, he's not necessarily that popular often at times because he's going to say, you've worked for so long on this item and it is not suitable, it is not meeting the customer's specification. So that has to be rectified either by reworking or starting again. So we've gone through how to insert them in SOLIDWORKS. There will be some exercises in your classes as well for doing that. So thank you for listening to this presentation.